forget the hype for a minute. We want to dig into the real foundations, the building blocks of artificial intelligence, machine learning, and deep learning. And what's really fascinating, I think, is how much of this stuff actually draws inspiration from, well, from us, from the human brain.
Exactly. Our mission today really is to give you a clear, kind of structured way to think about where AI comes from, how it actually works day to day, and, how it's shaping things. We'll trace the ideas, starting way back with the philosophical stuff, the father of AI, right up to these complex artificial neural networks. And we'll look at some amazing things they can do, but also, interestingly, what they still struggle with, going from the big ideas to the stuff you actually use.
All right, let's get into it. For those of you keeping track of all this, we hear these terms all the time. AI, machine learning, deep learning. They get thrown around a lot, sometimes like they mean the same thing. But are they really interchangeable, or is there a difference we should understand?
That's the perfect place to start, because knowing how they relate is fundamental. Think of it like Russian nesting dolls, maybe, or a Venn diagram. AI, artificial intelligence, that's the biggest concept. The overall dream of machines doing smart things that usually need human intelligence. Think robotics, expert systems, the whole field. Then inside that, you've got machine learning. It's a specific way to achieve AI. It's about systems that learn from data, they spot patterns, make decisions without being explicitly programmed for every single step. And then even deeper inside that is deep learning. This is a type of machine learning that uses these structures called artificial neural networks, usually with lots of layers. That's what lets them tackle really, really complex patterns in huge data sets. So yeah, connected, but definitely nested categories.
Okay, nested categories, that makes sense. And you mentioned the father of AI. We're talking about Alan Turing, right? His 1950 paper, Computing Machinery and Intelligence, that was kind of the starting gun.
Absolutely. Turing was thinking big, not just about calculation, but about intelligence itself. And he proposed this test, the Turing test, which honestly people still argue about today. The setup is pretty clever. You have an interrogator typing questions. They're connected to two things they can't see. One's a person, one's a machine. Their only job? Figure out which is which, just from the typed conversation. And Turing said, if the interrogator can't reliably tell the difference after a decent amount of time, well, then the machine should be considered intelligent. The really profound part is, it doesn't ask if the machine thinks like us, just if it can act intelligently enough to fool us. It makes you question, what is intelligence? Is it about the internal process or just the external behavior?
That's a huge question. And it's not just theoretical anymore. We've seen AI do some genuinely stunning things. Like AlphaGo, beating the world. Go, champion. Go. That game is supposed to be all about intuition, not just calculation like chess. And beyond games, AI is tackling problems that are just way too hard for humans. Complex math like symbolic integration, proving theorems, even helping with medical diagnoses, spotting things in scans sometimes.
Right. But here's the fascinating twist, what some people call the AI paradox. While AI crushes these complex, logical, often abstract tasks you mentioned, the stuff that seems incredibly easy for us, even for animals, can be unbelievably hard for AI. Think about like a squirrel navigating a park, dodging people, finding nuts, escaping a dog. That complex, real-time interaction with a messy world, still very hard for AI. Or just understanding sensory input, really getting what's in a picture or the tone of someone's voice, the sarcasm, trying to guess what someone else is thinking or feeling based on how they act, or working smoothly as a team. These are massive hurdles. This paradox, it makes you wonder if we're building the right kind of intelligence, or just a very powerful but different kind.
That's a really good point. Maybe the things we find easy are actually computationally harder in some ways. And like you said, AI isn't just in labs or sci-fi movies anymore. It's everywhere, often invisible.
Exactly. You're likely using deep learning multiple times a day and not even noticing. Those self-driving features in cars or the automatic parking, that relies heavily on deep learning. It's recognizing everything around the car, so the other vehicles, pedestrians, signs, processing it all instantly. Companies like NVIDIA are building the brains for that. Or think about your digital assistants, Siri, Alexa, Google Assistant, Cortana. They aren't just simple voice commands. They use AI to understand your natural speech, figure out what you mean, connect to your calendar, search the web, control your smart home stuff, and it goes beyond that. Services like Uber use machine learning, constantly optimizing routes, predicting where drivers will be needed, setting prices. You've got companies using computer vision, powered by deep learning, for things like security monitoring, analyzing traffic flow, PlateSmart and television, Sighthound do this, even robot vacuums. The Roomba 980, for instance, uses AI to map your room, avoid bumping into furniture, and learn the best way to clean it. So yeah, these examples really show how these concepts aren't just abstract theories. They're powering real tools. making things more efficient, more convenient, often without us even thinking about the complexity behind it.
It really is amazing. These everyday things are the result of those ideas we started with AI, ML, deep learning. But how did we leap from Turing's theoretical test to systems that can actually see obstacles or understand language? You mentioned the brain earlier. Is that really the blueprint? That's where it gets really interesting for me.
It really is. The core inspiration for a huge chunk of modern AI, especially deep learning, comes directly from neuroscience, from how our brains work.
Mm.
The basic unit in the brain is the neuron, the nerve cell. Think of it as a tiny biological processor. It has inputs, called dendrites, like little antennas catching signals from other neurons. It has a cell body, the soma, which kind of sums up and processes those signals. And then it has an output wire, the axon, which transmits the neuron's own signal onward to other neurons. And the scale is just mind-boggling. The human brain has something like 10 billion neurons, and each one connects to maybe 10,000 others through these junctions called synapses. That's where the signals jump across and get strengthened or weakened. Billions of neurons, trillions of connections.
Wow. Okay. So this incredibly complex, interconnected biological network, how do we even begin to replicate that artificially with artificial neural networks, ANNs?
Well, yeah, replicate is maybe too strong a word. Artificial neurons are much, much simpler mathematical models, sort of caricatures of biological neurons. An artificial neural network, or ANN, is just a network of these simple processing units. And what defines an ANN really comes down to three things. One, its architecture. How the neurons are connected. Are they in layers? Do signals only go forward? Are there loops? Two, its learning algorithm, the method used to adjust the connections. How does it learn from data? This involves changing the weights of the connections, how much influence one neuron has on another. And three, its activation function. This is the rule inside each artificial neuron that decides whether it should fire or send a signal based on the total input it receives, like an on-off switch, but often more nuanced.
And getting these ANNs to work wasn't like flipping a switch, right? It took a long time, lots of ups and downs. I remember reading about the early pioneers, like McCulloch and Pitts back in the 40s, just proposing the basic idea. Then Hebb talking about how learning might happen, neurons firing together, wiring together, and Rosenblatt's Perceptron in 58. That seemed like a big step. But then things kind of stalled for a while, didn't they? Until the big rediscovery of backpropagation in the mid-80s. That seems crucial.
Oh, absolutely crucial. Backpropagation was the key that unlocked the potential of multi-layer networks. Before that, we mainly had single-layer networks like the Perceptron, and they hit some serious limitations, which we'll get to. Backpropagation provided an efficient way to train networks with hidden layers, those intermediate layers between input and output. It figures out how much each connection in the entire network contributed to an error in the final output, and then adjusts the weights accordingly, working backwards from the error. It was a huge breakthrough. It showed that these networks could learn complex, nonlinear relationships, which was a major roadblock before.
So it's not just the individual neurons, it's how they're all connected and how those connections change.
Precisely. The power isn't in one artificial neuron, it's in the collective computation, happening across thousands or millions of them, all interconnected. And yeah, the architecture matters. You have simple, single-layer feed-forward networks, input straight to output. Then multi-layer feed-forward networks, with those crucial hidden layers enabling more complex processing. Still, information flows one way. And then you get recurrent NNs. These have feedback loops, connections that go backwards. This allows them to have a kind of memory to consider previous inputs when processing the current one. Really important for things like understanding language or sequences of events.
Okay, so we have these artificial brains inspired by real ones with different structures. How do they actually learn? You mentioned learning algorithms.
Right. Learning is the core process. And there are generally three main styles or paradigms of learning for ANNs. The most common is probably supervised learning. This is like learning with a teacher. You give the network an input, and you tell it the correct output it should have produced. The network makes a guess, compares its guess to the correct answer, calculates the error, repeat thousands, millions of times until it gets good at mapping inputs to the correct outputs. Think image classification. This is a cat. This is a dog. Then there's unsupervised learning. Here, there's no teacher, no correct answers provided. You just give the network a whole lot of input data. Job is to find structure within that data all by itself. Maybe it groups similar data points together that's called clustering. Or maybe it learns to represent the data in a more compressed, efficient way. It's about discovering hidden patterns. And finally, there's reinforcement learning. This is more like learning through trial and error with rewards. The network takes actions in an environment, like making a move in a game.
It then gets feedback, a reward signal, positive or negative, telling it how good that action was. Its goal is to learn a strategy, a policy, for taking actions that maximize its total reward over time. Think learning to play chess or controlling a robot arm.
Okay. Supervised, unsupervised, reinforcement, lots of ways to learn. Let's make it concrete.
Yeah.
That early model you mentioned, the Perceptron, can we zoom in on that? You said it was the simplest form.
Yeah, the Perceptron is a great example to understand the basics. It was developed by Rosenblatt using those McCullough-Pitts neuron models. It's typically a single-layer network, just input neurons connected directly to one output neuron, no hidden layers. And its main trick was classifying patterns that are linearly separable.
Linearly separable. What does that mean exactly?
It means you can draw a single straight line or a flat plane in higher dimensions, a hyperplane, to perfectly separate the two different classes of data points you're trying to distinguish.
Okay. So how does it draw that line, metaphorically speaking? Well, each input signal coming into the output neuron is multiplied by a weight. You can think of the weight as representing the importance or strength of that input connection. All these weighted inputs are then summed up inside the output neuron. Then, this sum is compared to a threshold value. If the sum exceeds the threshold, the neuron fires outputs a 1, say. If it doesn't, it outputs a 0. Learning in her perceptron involves adjusting these weights and maybe the threshold based on the errors it makes until it finds a combination that correctly separates the data, effectively finding that dividing line.
Right, and the source material gave examples with basic logic gates like A and D and OR. That helps visualize it. For an A and D gate, the output is 1 only if both inputs are 1. So you could set the weights W1, 1, W2, 1, and maybe the threshold to 1.5. If both inputs are 1, the sum is 11 plus 11, or if 2, which is greater than 1.5, so output is 1. Perfect. Any other input combo, 0, 0, or 1, 0, or 0, 1, gives us sum less than 1.5, output 0 works. Exactly. And for an OR gate where you want a 1 and 10, if either input is 1, you could keep the weights W1, W2, 1, but just lower the threshold, say, to 0.5. Now, if input is 1, 0, sum is 1. Greater than 0.5, output 1. If 1, 1, sum is 2. Greater than 0.5, output 1. Only 0, 0 gives a sum of 0, less than 0.5, output 0.
So just by tweaking the weights and threshold, this simple structure can implement these basic logical functions. It finds the right line to separate the ones from the zeros.
Precisely. But connecting this back, this also highlights the perceptron's big, famous limitation, the XOR problem, exclusive OR.
Ah, XOR. I've heard about this. That was a problem.
It was a huge problem. XOR means the output is 1 if the inputs are different, at 0 and 1 or 1 and 0, but 0 if they're the same, 0 and 0 or 1 and 1. Now try plotting those 4 points. You'll find you cannot draw a single straight line to separate the points that should output 1 from the points that should output 0.
Oh, right. You'd need like 2 lines to fence off the right areas.
It's exactly. And a single layer perceptron, by its very definition, can only draw one line. This failure wasn't just a theoretical curiosity. It was famously highlighted in a 1969 book by Minsky and Papert, and it led to a massive loss of funding and interest in neural network research for years, the first AI winter. It showed that these simple networks couldn't handle even slightly more complex, nonlinear problems. It really forced the field to eventually develop multi-layer networks, the ones that can learn those complex boundaries, paving the way for modern deep learning.
Wow. So that simple XOR problem almost killed the whole field. That really puts things in perspective. Okay, so wrapping this up, what does this all mean for us today? We've gone from Alan Turing asking, can machines think? Through the different layers of AI, ML, and deep learning. We've seen how they're inspired by the brain's structure with artificial neural networks. We've seen them working in our cars and phones and understood the basics of how they learn, like with the perceptron, and even hit some of those early walls like XOR. It's been quite a tour.
It really has. And understanding this journey, the Turing test's philosophical weight, the AI paradox showing the difference between human and machine strengths, the biological roots of ANNs, and even the historical significance of roadblocks like XOR, it all gives us a much richer context for where AI is now. It shows it's not magic, but a field built on decades of ideas, breakthroughs, and overcoming limitations. It really sets the foundation for understanding the more advanced stuff happening today, and maybe something for you, the listener, to think about. Reflect on that AI paradox. Why are some things easy for us but hard for AI, and vice versa? And consider that struggle with XOR. It took a fundamental shift to multi-layer networks to solve it. What do these kinds of fundamental differences, these historical hurdles, tell us about what human intelligence actually is compared to the artificial kind we're building? And how could really understanding those differences help us guide AI development, not just to make more powerful calculators, but perhaps machines that are genuinely more adaptable, maybe even more intelligent in a way we truly recognize? Something to mull over.